Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Carl Carlson.
And this is Fred Schenkelberg.
Hey, Fred.
I'm going to make an assumption you got something on your mind you want to talk about, because we didn't really talk about it too much before we started.
I'd be careful about what assumptions you make there, Fred. Fred and I were talking today. before hitting the record button about how often assumptions go unnoticed. They just sort of happen organically, or people have always done it a certain way, and they're not consciously realized. And then you end up in a problem because of wrong assumptions. And it's just pervasive. And it's almost everything I do that's in reliability has assumptions that are involved. And, I'll just start off with a 30-second story. In one of the reliability classes I've taught, I had this module of data from NHTSA, National Transportation Safety Association, of fatalities. And part of the database is airplane fatalities, and part of the database is vehicle fatalities. And it's all the same data. And then I proceed to prove to the students that airplanes are safer than cars. Mm-hmm. And then in the next set of slides, I prove to the students that cars are safer than airplanes. And they both look logical, and the students are going, what? How could that be? Mm-hmm. And it all is based on assumptions that I don't disclose as I'm analyzing data.
Right.
And that experience has taught me that, and of course you get into, using mean time between failure, and there's a million things that we get into in reliability that have baked in assumptions. I thought it'd be fun just to talk over the subject as to how do you manage and navigate the subject of assumptions when you're doing reliability work.
Yeah, the first thing that comes to my mind is very early in my career, I was in a group that we ended up doing lots and lots of training. And I was in a class, a bunch of the engineers were in a class on measurement system analysis, gauge R&R in particular. And I'm talking to one of my, the quality folks about it. And they said, yeah, we're having a real problem in the lab. And we really don't know what's going on. Can you come down and take a look at it? Maybe what you're learning will help. I said, okay. And the product we were making at the time was this heating cable, and it was temperature sensitive. So they would roll these big reels and all these products into a temperature controlled room and let it set overnight to come to temperature. And in the morning, they go through and they'd hook up leads to the wires coming out of these products to measure the resistivity, basically. And depending on the particular product, it should be within a certain range, and then it was considered good, and they put a green sticker on it. And if it wasn't there, they put a red sticker on it, call it bad. And they were running into a significant increase in bad products. And they said, we don't know if it's our measurement method. And so I said, well, that's a perfect class example to go try it. And they had two carts, and the leads on one cart had a blue dot on it, and the leads on the other cart had a green dot on it, on the hinge of the clamps. And one of the things I learned in that class is question everything. In every step, every part of the process, understand it. If you're assuming that you're measuring with the same equipment, check it. It was trust nothing. It was kind of the mantra in the measurement system analysis class. And so I saw that difference, which I asked them about it, and they go, oh, what do you mean? Oh, yeah, that is different. But they're the same. They're the same size, same brand, all these kinds of things. They're the same. It says brands typically don't put different dots on it just for fun. And so we questioned it. We went back to the catalog, and one was a 4-point probe, which means that the contact resistant wasn't included in the measurement, which is a big source of error and measurement error when you're measuring resistance, for example. And the other probe, the one that we eventually figured out was the source of all their problems, was a 2-point probe, which meant that the contact resistance was included in the measurement of the product. And depending on how hard you make contact, or how well the metal-to-metal contact was made, it dramatically changed the amount of resistance. And so I said, well, let's measure this. You get a bad one. Let's use the other one for a second. And that was good. And what if you really clamp down hard on this? And like, oh, okay, now it's good. And it was, the assumption was when they had whatever reason they needed to replace those clamps, those probes, they just bought one. They didn't, it was part ignorance, but it was also part not checking. I don't think they knew the difference. The technicians I was working with didn't really know the concept of 4-point probes and 2-point probes for measuring resistance without contact resistance in it. So sometimes assumptions are just ignorance. I don't know to ask that question. Whereas it can be combated with, we make assumptions all the time. And like you said, Carl, many times it's unconsciously done.
Well, and that's where your comment about questioning everything is so important, because you may, as a engineer in a meeting, or you're having a discussion with people, they're describing something, and maybe you don't understand it fully.
Mm-hmm.
And the problem is people don't want to be embarrassed. They don't want to show their lack of knowledge, that kind of thing. So the ego gets in the way. But a really smart person questions and doesn't worry about whether you look silly or not, because that's how you learn and that's how you get above it. And you will find oftentimes by questioning the unconscious assumptions that go into something. I have a story to tell. I did, back in my early days, I attended a number of classes on Weibel from Dorian Shainin, the father of the Shainin
Mm-hmm.
family, and he was amazing, really, really smart. I learned Weibel from the ground up. This is back before, when we used flimsies, and
yeah, and you had Weibel plotting paper.
yeah, exactly, Weibel plotting paper. And so he would pass out the paper and we would plot. So we learned, shape parameters and scale parameters and everything else, all from the ground up. And so I had a pretty solid knowledge of fundamentals. Then I moved on to a different job, and I attended a class, and I'm not going to say names here, but I attended a class just to sort of audit and participate and see what it was like that was teaching Weibel. And the instructor was pretty good, except they didn't really like questions. And so we had the what is it, the paper clip.
Mm-hmm.
And you remember, you start twisting the paper clip,
Yeah.
and then you count the number of times, and everybody does it, and then you plot
Yeah.
the number of times until it breaks. And I raised my hand. I said, what if one of my twistings goes a little too far? In other words, I'm thinking for the metal clip, I'm in the yield portion of the curve rather
Right.
than the pre-yield. And he looked at me and says, that's a dumb question. He's basically
And then he shuts you right down.
basically
Right.
just do your, twist it and give me your number. And I blew it off. So the instructor had some assumption baked into his presentation about the plotting the Weibel distribution, failure distributions related to these paper clips. And the assumption obviously had to do with the data point has to be within the whatever the material is that you're exercising, stays within the plastic, doesn't go into the yield portion of the curve. But it was just interesting how that assumption was not openly discussed, and
Mm-hmm.
how often that happens. I have one other real quick one then is when we did a lot of early reliability work at General Motors, we had to develop reliability requirements because they weren't really prevalent. They weren't very good, frankly. I broke down the famous 4 elements of reliability. The probability that you're achieving the intended function, under certain operating conditions over a period of time.
Right.
And and I basically separated those out because some of those were just being assumed when people talked about reliability. Reliability is 95%. Well, what are you assuming with that? Well, we're assuming that the operating conditions are XYZ. We're assuming that the the part accomplishes its intended function, which is defined. All these different things.
Oh yeah, but you run into it way too many times. They say, well, it's a 10-year product, right? Well, how many should last 10 years? And you get 20 different answers, and vice versa. It's a 95% reliable. Right? All right, for a
Yeah.
day, for a week, for a month, for one drive to the store, over what duration? Oh, we get lots of answers for that. It's tough.
Yeah. And so if there's one message to get across with people is make your assumptions visible, surface them, write them down, agree upon them, make sure that everybody is on board with the assumptions you have going into an analysis or into a project. That's the safe thing to do.
Yeah, this is the safe thing to do, and I really appreciate Wayne Nelson, his book on accelerated testing, which is getting old now. Yet I go back, I've worn out the first copy I had. It just fell apart.
Mm.
I bought another copy years ago, and it still serves me regularly. But one of the things he does that I don't see in many other textbooks on statistical reliability engineering statistics type stuff is, well, what are the assumptions and how do you check them? And it's been a pet peeve of mine that Reliasoft, for their Weibull analysis, did not make the regression or the residual analysis easy to do. You could do it, but it took superior effort. You really had to really dig to even get to these numbers. And the idea is that whatever the statistical process is, and what I liked about Wayne's book, he says, all right, we're going to use the log normal distribution and we're going to do this, this, and this. But right at the start of it is this only applies if you meet these three criteria. These three assumptions have to be valid. That this is the residuals are normally distributed, that they're independently each failure is not contingent on, for example, on a car, that tread wear on the two rear tires are probably similar. So the time to failure of one is seeing the same patterns as the other one. Those are not independent anymore. So if you're looking at tire wear, they got to be on different cars. You got to be on different systems. Otherwise, they're dependent on each other. One forecasts the other one in a way. But he went through 3 or 4 different assumptions for each of the types of analysis that he described in the book and said, this is how you test it. Here's how you make sure that it's good enough. And in conversation with him, he said, there's a bunch of other assumptions that are a little bit more loose. If you don't really need it, it's still okay, kind of thing. He says, so I didn't include those. But these ones, if it doesn't meet these, your analysis will give you a number at the end of the day, yet it will be less than meaningless. It'll be misleading.
Exactly.
I mean, like, I'm thinking of statistical process control. You do an X bar plot.
Mm-hmm.
And so many people I've talked to about SPC is that, why do I need to take 5 samples or 10 samples or whatever for each measurement? And I said, because the central limit theorem allows us to create the control limits. And they're looking at me like, what? What's that got to do with SPC? Okay, let me explain.
There's just so many stories come to mind, Fred. They're just flashing around with me on the whole subject of assumptions. Like working at General Motors, we spent a lot of money testing vehicles.
Mm-hmm.
Very expensive and very time consuming. You can imagine that if by the time in the product development process that you have vehicles to test, you're well on your way to having frozen designs in a lot of places and things, or you just
Right.
have an extremely long product development process.
Right.
So one year, the top management said it's too expensive. we just can't keep doing this. It takes too long. We want fast to market. We're not going to do the same kind of vehicle testing that we've done.
Well, that works if, especially it's smart to do if you're never using the results of that testing to do anything, then it really is a waste of time.
Yeah. And the problem that I ran into was we had to understand what assumptions go in. Okay, we're going to move to lab testing instead of vehicle testing.
Mm-hmm.
That'll work if you make the right assumptions.
Right. And you use that door closing test, and I've run into it with button pushing, is you set up a system like a pneumatic system or a robotic arm or whatever that repeats the same motion with the same force all the time. But you and I both know is that an 8-year-old's going to swing on that door, and other people are going to use it as a lever to push themselves up or down, out of in or out of the car. Other things are going to get in the way and interfere with the door closing correctly or not. And my seatbelt strap on my car seems to be the habitual interference with the door closing. Though every step we make away from how a customer actually uses your product is rife with assumptions about what do we focus on and don't focus on. Because
Yeah.
is dust an issue or not? Well, if we don't add dust, we're assuming it doesn't.
So let's stipulate that we're basically having to make assumptions.
Yep.
Because you're not going to test in an environment where you have the actual environment with the actual parts and the actual time for 10, 15 years. You're going to make certain assumptions.
Mm-hmm.
But the whole point that I want to make to the listeners on this is that let's make those assumptions visible and make sure they're rational. We know there's a little risk when you go into accelerated testing.
Yeah.
We know there's a little risk when you go into fast to market. Let's understand what the assumptions are, and then we can clarify and characterize the risk involved with it.
And whatever you do, don't use 0.7 electron volts as assumed activation energy. just don't. We're going to assume it's that, or we're going to assume it's in the flat part of the curve. Like, stop.
And don't assume there's probably a list of the top 10 don'ts.
Yeah, that's probably going to be an article in my No MTBF series.
Yes, exactly. So here's a don't. Don't assume that people are going to use the product exactly as intended.
Yeah.
There's going to be some level of abuse, like you say, the child hanging on the door. So try to be reasonable about what is the anticipated abuse of a product. So you don't want to make that mistake.
Mm-hmm.
Here's a story. Let's see if the listeners can get this one. Working on a transmission system for a garbage truck that was called brake energy recovery system.
Okay.
And as you put the brakes on in the truck, there was a bladder that basically just took on some of the energy.
Okay.
And then we use that energy for acceleration. So
well, that's cool.
Brake energy recovery system. Very cool.
It's a lot easier if you did electronics, if you had an electric engine and
yeah, that's right.
generate electricity to recharge it every time. That would be easier. That was before that time.
So I was brought in for a reliability plan and make sure they're doing this reliability testing properly and stuff. And the first thing I read, like they're testing their prototype system, which is kind of not the right time to bring in a reliability person, but they did. And so they're testing. I go, okay, what are you testing the bladder? How are you testing it? Well, we anticipate the maximum the bladder would receive would be 5,000 psi or something. I forget what it was exactly. Some maximum. I said, okay, so what are you testing to? Well, we're testing to 5,000 psi. Do you have any safety factor on that? What do you mean?
What if it goes to 5,001?
Yeah, exactly. So I said, well, you want to let's talk about safety factors and probability functions and failure distributions, things like that. Turned out before we could actually make a change on the requirements, they had an explosion on the bladder because it got just over 5,000.
Oh, geez, so hopefully it didn't hurt anybody.
Yeah.
5,000 psi blowing up is not a good thing.
So what was the assumption? What was the wrong assumption that should have been surfaced about that? And that's what I'm basically asking the listeners.
Well, this goes way back to your paperclip thing, because if I had that problem and I don't want to sit there and flip this paperclip open and close a bunch of times, I would just take it and twist it 375 degrees and it'd come right off. And I mean, one cycle.
Yeah, exactly. So there are some assumptions that go into every analysis. The question is get them visible and then decide if they're correct or not. Are they rational? Do they make sense as assumptions? The ones that come back to bite you are the ones you're not looking at.
Yeah, and it also helped you communicate more clearly. This is what this analysis can tell us and not tell us. These are the assumptions underlying it. If those aren't true, then this analysis isn't good. And so there's multiple layers of it. And we talk about it in the book, Carl, when we talk about the key decisions is we don't just assume that the program manager is interested in a precise estimate of this failure mechanism. Ask her, what do you need to know to make your decision? And we stress that over and over is that don't assume, find out what they need to know and then get those results to them and check all of those assumptions as you go through. And the trade-offs, there's always trade-offs. And part of it is that it's the ones that are not, like you said, the ones that are not articulated are the likely source of real problems and poor decision making later. And it's just prudent engineering to think through all those and to articulate them so that they're understood through the group. Now, you don't need to list every single assumptions like I'm assuming the sun's going to come up tomorrow.
Yeah, good point. Good point. You want to get at the major ones, the primary
Yeah, that's why I
assumptions.
look at Wayne Nelson and he said, well, here's three or four that if it doesn't meet this analysis doesn't apply. And so you need to think through what is it needed in the test setup or in the analysis part or in the quality of the expected outcomes. Think those through and make sure they're communicated so that you and others can say, well, no, that assumption's, I think we're good on that. Here's the proof of it. Yet, have you thought about this? Oh, okay. I hadn't thought about that. There's this different failure mechanism that occurs. All right.
Here's an easy one for people. I'm thinking of a time I was consulting with a company that designed trucks, design and built trucks, and basically 15-year life. And we were going into the test program, the reliability test program, and they said they have a few trucks that they're testing. They do run through all the tests and everything. How long do you test them? 1 year. Well, how do you determine whether you meet your reliability? Well, that's simple. We count up the failures and multiply by 15.
Yeah. You're assuming nothing wears out.
Yeah.
Or did I just steal the thunder on that one?
I mean that's an easy one, but they didn't see that going in. They were basically convinced that they'd had some textbook that said, when you have a system, it's going to be an exponential distribution. It's going to be in that
Not part of
portion
the
of the
curve.
bathtub
Yeah.
curve.
Yeah.
And so you just multiply it out, and now you know how many are going to fail in 15 years. And I said, no, that's not going to work. So we had a nice conversation after that. But once again, the unknown assumption, the undiscussed assumption, and that's one of the jobs of, I think, of a reliability engineer, is to be aware of when people are assuming things that they shouldn't assume.
Yeah. Yeah. No, very well said. So, but now I will make the bold assumption that at some point we're going to have to end off this podcast and ask our listeners, like you said, Carl, is what are the things you've seen and what kind of assumptions that you've saved somebody from making a poor decision off of, or that have you've learned the hard way that you can't ignore. The idea is that, and to stay on this bad track of making assumptions, is I'm assuming that you probably do have something on your mind, and that letting us know allows us to chat about it and talk about it, and you and our peers can all learn from it. So that's my bold assumption for the show.
Good way to round off. So
Yeah.
So please do let us know what you'd like to know more about on this subject. If you've had any interesting stories about unknown assumptions or missing assumptions, things like that, I'd love to hear from you.
Love to hear it. And they should go over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us there. And Carl and I and the other hosts of the show are available on LinkedIn and our About pages. So plenty of ways for you to get in touch and participate in the conversation. And we'd love to hear from you. And you don't have to assume that. We actually do enjoy it when we get comments and questions and stuff.
Very
So with
good.
that, I think we'll, like you said, we'll round it off and call it a day. So thanks so much, Carl. And I'll make the one last assumption that you have a great rest of your day.
Yeah, thank you very much. Nice talking to you, Fred.
Thanks, Carl. Talk to you later.
Bye-bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.